Moles and states of matter. Okay, so let's get into this. In the last video, I introduced the relationship between moles and chemical equations. And this was done in a way to think of chemical equations uh, as recipes where where the quantities are measured in moles. Okay, and the coefficients eventually represent the number of moles per recipe. So when we looked at the previous problems with the combustion of propane, uh, the um, the coefficients we said could be represented as moles per recipe. So in that chemical reaction, there was a 5 in front of the O2, so we could just, what that represents to us is that every time we do that reaction, we need 5 moles of oxygen. Okay, in relation to everything else. Okay, so then we see that moles cannot be used practically in measuring. Okay, so if we say we need 10 moles of oxygen, we can't go out and measure 10 moles of oxygen because it's impractical, because they're just that's too large of a number. And but what we do know is that we can figure out how much 10 moles is because we know of the mole mass relationship. In terms of that relationship, we know that for every 1 mole of oxygen, that's O2. So 1 mole of O2 has a mass of 32 grams. Okay, and if I have 10 of them, I do 32 10 times, and for 300 I get 320 grams of oxygen, which is the same as 10 moles of O2. Okay, so we have a way around it to even though we can't use the moles in the chemical formulas, we have a way around it to figure out the moles given the mass. Okay, however, there's times where we can't measure mass, or it's impractical to measure mass to find moles. So now we are going to look at other ways to determine moles from other states. So mass is a really good way to measure the mass of solids. Okay, so so you could just weigh it out on a scale. We have sodium chloride, and you need so many moles. You figure out how many grams that many moles is, and then just weigh it out. Okay, that's simple. Okay, but there's other time it's impractical to measure out the mass of a material because of its state. And that's what we're going to do here. We're going to go over the different states and how we can figure out the moles for each state in the practical way that doesn't often use the relationship between mass and moles. Once we get done with this video, what we're going to do is to actually apply this to chemical equations. All right. What we do is we could start out a chemical equation with everything's in the same state, like we did in the previous video with propane. But that's not always going to be the case. Actually, often what you do is you'll have more than one state in a chemical equation. And what you're going to have to do is you're going to have to figure out the moles of a substance, not from mass, but from like volume or other measurements. Okay, so that's what we're going to learn here, is how we can figure out the moles of a substance based on its state. So just go back. So we talked about solids already. Okay, from the previous PowerPoint. If we want to find moles from grams, we simply use the molar mass. And what it comes down to is, you could do dimensional analysis and everything, but what I'm going to do is, if we want to figure out how many moles, so how many moles per how many moles I have given a mass, what I'll do is I'll take, so if I'm given a certain moles mass, and I want to find out moles that is, I'll just divide by the molar mass. And if I want to find out how much mass I have from a given moles, I multiply it by the molar mass. Okay. Like, if I have 10 moles of O2, how many grams is that? Well, each one is 32. I do that 10 times for 320 grams. Okay. The other way around, if you have, let's stay with O2. If you have, I'm just using big numbers here. So if you have 160 grams of O2, how many moles that is? Well, you divide that into groups of 32 for 5 moles. Okay, and that's what I try to do is that just remember this relationship, and it's simple. Okay, instead of writing it all out, but writing it all out and getting all your units and everything is a good way to do it if you really want to check your answer. But you really should get to the point where you understand from mass to moles, mass. It's basically grouping and ungrouping. Okay, so let's look at the other states of matter, and the first one we'll look at gases. Gases, well, you can measure the mass of a gas, and it'd be simple. What you do is just take a tiered container. That means you've zeroed out the container, and you weigh it. All right, and then you can if you know the molar mass, you can figure out the amount of moles, and that's simple. You can do that. What you do is there's one reaction. What you do is you can take like hydrochloric acid and zinc, and this is the single replacement reaction, and it releases hydrogen gas. And what you can do is if you have if you have the reaction take place in a Erlenmeyer flask, you can simply put a balloon over the Erlenmeyer flask, and as the gas is produced, it will fill the balloon, and then you seal off the balloon and you weigh it. Okay, and as long as it doesn't float away. Okay, but often it's impractical to measure the mass, and it's a lot easier to measure the volume of a gas. Okay, and so what we like to do is, what is the relationship? So if I measure the volume of a gas, or pressure, but usually volume, how can I find the number of moles given the volume? Okay, so again, going back to previous example, I fill up a container, and then I watch displacement of water being from a container, and I can measure the volume of the gas that's being produced. So let's say I collect collect 3 liters of gas, and doing some of oxygen gas. And remember, it really doesn't matter what gas we use here, because what we're going to do is use the ideal gas law. And the ideal gas law says all gases, no matter what they are, but who they are going to behave the same. And when we use the ideal gas law, so even though this says 3 liters oxygen gas, it could be anything. All right. And the reaction is at a constant pressure, which I would say is 1 atmosphere, and the temperature is 20 degrees C. And that's about 70 degrees Fahrenheit, which is room conditions. So I want to find out how many moles that is. Well, simply, I use the ideal gas law, because the relationship says if I know volume, I can figure out moles, N. Okay, that's given that I know pressure, temperature, and the universal gas constant. So you simply just solve for N, the number of moles. Okay, there you go. And when you do that, the liters cancel out, the atmospheres cancel out, and the temperature cancel out, and you end up with 0.125 moles of O2. Okay. All right. So if a chemical equation says you have 3 liters and you want to find out how many moles that is, okay, and then we apply that to how many recipes, this is how you would do it. Okay, now we have to be able to do it the other way too. So if you're given a certain amount of moles, like we will apply this in terms of the chemical equation. So in a chemical equation, you can figure out how many moles of a substance you make. So what you want to do is find out practically what that mole is measured in. Okay, in this case, um, liters. Okay, volume. So one way. So this one up here is going from liters to moles. Okay, and this one here will be, if you start out with moles, you can go to liters. Again, we're going to use the ideal gas law. So let's say I have, what is the volume of 2.5 moles of N2 at 1 atmosphere and 20 degrees C? Well, now they solve for volume. Okay, plug everything in, and you get that 60.14 liters of your gas, N2. Okay, so when you see a gas in the ideal, in a chemical equation, you will be using the ideal gas to figure out how that is. And we're also going to see that there's really kind of a cool relationship that sometimes you don't even have to do the ideal gas law to figure out how much gas you have. And we'll go over that when we talk about stoichiometry of gases. Right, so there's gases. That's simple. So we got solids, which you measure out mass, and you're using molar mass. You can figure out moles, and the other way around. If you have moles, you can figure out grams using molar mass. For gases, we use volume as a way of measuring, and so we can figure out moles using ideal gas law and going to reverse as well. Okay, liquids. Again, we could just weigh out our liquid, find the moles using the molar mass, but this is but a practical method is not to do this. Okay, okay, it's not to weigh out your liquid, but it's to actually measure. You again measure volume. All right. So, when we measure out liquids, we typically use graduated cylinder or some other device. And so, what we'd like to know is using moles to volume relationship. Now, we just talked about gases, and gases we saw the same thing, volume to moles. Now, you may want to think, you go, oh, I can just use the ideal gas law. No, don't do that, okay? Pay attention to the states. If the states say liquids and you're finding, therefore you're going to be using volume, do not use the ideal gas law. Okay, slight interruption there. I had to answer phone. Okay, so when we use liquids, and we want to find volume, do not use the ideal gas law. So how are we going to find the relationship between volume and moles for liquids? Well, for liquids, what we're going to do is use density. And it's going to be an indirect relationship. It's not a one step, okay? You're going to be doing 2 steps. Density, and we're going to use the relationship. Density is mass per volume. And the units we'll usually use are grams per milliliter for liquids. Okay, so if you look at this relationship, mass and volume, we see that this gives me a link. So if I'm given volume, I can figure out the mass. All right, because density gives me the relationship between mass and volume. And then once I know mass, what I can do is use molar mass. Okay, so For liquids, you're going to have a two-step process, okay, to figure out moles. For gases and solids, it's just one step. So the first thing you do is you're going to find out, you're going to have the relationship between, you're going to find out grams using density, and then that's if when you're given a volume. So let's say it's given a volume. So first step you're going to do is find the mass using density. And then using molar mass, you're going to find moles. Okay. So first step, second step. And then we're going to see going the other way is the same. Given moles, you're going to figure out mass using molar mass. And then figure out volume, use density, but reverse, and find volume. And so we're going to. Okay, so the first one we're going to do, find moles from volume. So we're going to start out with a volume. Okay, and then go to grams using density, and then go to moles. Okay, to figure using molar mass. Okay, so density, molar mass. Okay, so I'm given 253 mils of liquid octane with a density of 0.72 grams. And what we're going to do is I'll go over the three methods, three mathematical methods, and you can use any one you want. Just make sure you get the right answer in the right units. So if you use ratio, it says x grams per 253 mils has to equal 0.72 grams per mil. And then you simply solve for x, okay, and you get 182.16 grams of octane. If you use dimensional analysis, DA, you do a 253 times the conversion factor. So you can set this guy up so the mils cancel out. And again, you end up with 182 grams of octane. Okay, now for grouping, the grouping is mils, all right? And so what we're going to do is, so what we want to do is go to grams. So what we're going to do is we're going to, we're going to go from grams. So where is 0.72? So if we have 0.72 grams per mil, and I have 253 mils, so every mil has 0.72 grams in it. So what I'm going to do is 0.72 grams 253 times, and that's equal 182.16 grams. So anyway, it's fine. It gives you the same answer. This one to me is conceptually right, but I probably would do these two because they're quicker. All right. Now I have 182 grams. Now I want to figure out how many moles that is of octane. Well, I know the molar mass of octane is 114. So octane is C8H18. All right, so 8 times 12 is 96. 96 plus 18 is 114. So each one is 180. So 182.16 is my mass. I'm going to divide that by 114 to figure out how many moles. And so it's 1.6 moles of octane. Okay, now let's go the other way. So I want to figure out how many mils from moles. All right, so I'm going to start with moles. And I'm going to figure out how many grams using molar mass, and then I'm going to use density to figure out volume. All right, so let's say I start out with 1.5 moles of liquid pentane. It has a density of 0.87 grams mil. So first thing I have to do is figure out how many grams that is. So I know 1 mole is 72 grams per mole. I have 1.5 of them. So 72 1.5 times is 180 grams. And you could, dimensional analysis ratio, but this is just remember a quick way to figure out moles from mass, okay, and grams from moles is use how to figure this out. So moles times molar mass is how many grams you have. So now I have 108 grams of pentane. Right. The density is 0.87 grams, and we could go over other different ways to do it. I know that use the ratio x mils per 108 grams has to equal 1 mil 0.87. Solve for x, you get 124.1 mils. Dimensional analysis, you set it up 108 times the conversion factor, 124. And for grouping, what you're going to do is group the 108 into groups of 0.87, so you can divide 108 by 0.87 grams, and you also get 124 mils of pentane. Okay, so that's how you figure out. Given a liquid, you can figure out moles from volume, or you can figure out volume from moles. And again, when you use this in stoichiometry, chemical equations, this is why one of the reasons why states are important when you write them out. So when you write out the state of the chemical equation, you need the states because you're going to have to figure out how you're going to measure out your moles, and also how you're going to measure out your substance. Okay, so now we're going to move on. Okay, now the next state, so we have, right now we have, if you're given solids, you just weigh out, you figure out the molar mass. Figure out the mass using molar mass, and vice versa. Okay. For gases, if you have volume, you can figure out number of moles using the ideal gas law, and vice versa. For liquids, you need density and molar mass. It's a two-step process. And you need to figure out, then you can figure out, if you have volume, you can figure out the mass using density, and then for the mass, you can figure out moles using molar mass. Okay, now the last state is aqueous solutions, and it's technically not a state, okay, but we write AQ to represent that something has been dissolved in water. So before we go in to figure out the relationship of figure out moles of an aqueous solution, okay, we first of all have to know how an aqueous solution is measured, and first of all what it is, and then how is it measured. Okay, so aqueous solution. So what does this mean? Okay, first of all, what is a solution? Well, a solution is a homogeneous mixture made from a solvent and a solute. The solute is what is dissolved, and the solvent is the dissolver. Okay, in the case of aqueous solutions, the water is the dissolver or the solvent. The solute is the thing that's being dissolved, and it could be ionic compound like salt, NaCl, or whatever material used ionic. It could be acid, or it could be any other substance that dissolves in water as well, like glucose, sucrose, and etc. Ammonia. Okay, so the key component of an aqueous solution is the solute, okay, the thing that's being dissolved, and how much of it there is in terms of moles. For instance, this 2 moles of sodium chloride per liter of solution. So this says 2 moles of solute per 1 liter of solution. Okay, now one thing to notice about this right here It does not say 2 moles of sodium chloride per liter of solvent. And this is an important point. Okay, to understand solutions, it is good to see how we make them. So I just said that it's solute per solution, not solute per solvent. And this is actually, well, so let's go over how we make a solution, and you'll see how solution is different than solvent. So so let's say I want to make this solution right here where I have 2 moles of sodium chloride per 1 liter solution. Here's how the steps I do it. I measure out 2 moles of sodium chloride. Well, sodium chloride is a solid, so I have to know its molar mass, which is I'm around 58.6 grams per mole. And if I have 2 moles, I simply measure out twice that, 417.2 grams of sodium chloride. Okay, so I got this in a container. And now what I do is I'm going to take a beaker. In this case, maybe I take like a 2-liter beaker. Okay, it's 2-liter beaker. And what I do is I put somewhere between 1/2 to 0.8 liters of water. So if this is 1 liter here, I'd only fill it up to about here with water, okay? And the water should be distilled or as pure as we can get. Okay, notice I don't fill it up to 1 liter. The reason why I don't add it to 1 liter is because when I add the sodium chloride, if this is 1 liter, what that's going to do is it's going to cause the volume of the whole volume to increase. And when I want the volume of the solution, that is the water and the sodium chloride, to have a final volume of 1 liter. Okay. Okay. So the way that you usually do it is you you add about somewhere between for every liter you add about whatever your final volume is, you add between 1/2 to 3/4 of that volume, right? Okay, so I have, let's say I put in 700.7 liters of water. Then what I do is I put the 117.2 grams of sodium chloride in it, mix it up really well so it's all dissolved. Okay, so you dissolve it, and then what you do is the final step is you add enough water to bring up your final volume up to 1 liter. So what you have is 2 moles of sodium chloride in 1 liter of solution. Okay. Now, if we were in a lab, we would actually do this. Okay, we'd show you how to do it. And this is really good. This is a really good thing to know, especially if you go into chemistry. If you go into work in a lab, especially if you work with biology or biochemistry, you would be making many solutions. And this is how you would do it. You take your whatever your volume is, you take somewhere between 1/2 and 3/4. Add your appropriate amount of solute. Okay, mix them up, and then bring it up to the appropriate volume. And by the way, we wouldn't use a beaker to get the final volume. We would use a volumetric flask, more than likely. Okay. So aqueous solutions have unique, not generic, terminology. All right, this is terminology. We have moles per liter solutions, moles of solute per liter solution. Okay. Now, instead of saying all this, what we do is we have a word to represent this whole statement here, and that's called molar. All right. So 2 moles of sodium chloride per 1 liter solution is also known as 2 molar NaCl. And that could be simply written as 2 big M NaCl. Okay, so 2 molar means 2 moles per 1 liter solution. Okay, this is known as molar concentration. And again, a short word for molar concentration is molarity. So what we would say is the molar concentration, or the molarity, is 2 molar, 2 big M NaCl. Okay, so you'll hear, as we go through these, you'll hear interchanging. We'll be interchanging moles per liter with molar and big M. You'll hear molar concentration and molarity interchange as well. And I just do it naturally because I've been using it so long. So pay attention to that. Okay. So mixing solids into water to make aqueous solutions. So let's say I want to make an aqueous solution, and so let's say I want to make 4 liters of 3 molar 4 liters of a 3 molar solution of silver chloride. So what I'm going to have to do is find out how many moles of silver chloride. So what I'm saying is how many moles, I'm asking, is how many moles of silver chloride are in 4 liters of 3 molar AgCl. Okay, and then how many grams. Okay. So before we do any math, let's just see how it works. Okay, so you have 4 containers. I mean, we'll do the math, but conceptually it makes sense. And each one, so each one is a liter, and each one has 3 moles per liter. M, and let's see how that works out. So how many total moles is that? Well, that's 12. Okay, and then how many grams? Well, you figure out how many the molar mass of HCl, and then multiply that by 12, and you get that amount. Okay, let's do the math. Let's see how that all works. So what you do is you change 3 molar to 3 moles per liter. And just like I said over here, you have 4 liters of 3 moles per liter, so you have 12 moles of AgCl. And you could use dimensional analysis or whatever to figure it out, but it just plain makes sense. Okay. Now, a quick way to know this is to figure out moles. You can simply do volume times molarity. Okay, and this will be used a lot. Okay, so moles, for solutions, is equal to volume times molarity. Okay, big M. And that's what we did up here. We took volume, okay, 4 liters. There's 4 times the molarities, 3, 3, and 3. Okay. All right, and then what you have 12 moles. Each mole is 143.6 grams. You simply multiply that by 12, and you get this. So this is used a lot in stoichiometry. Okay, when you have aqueous solutions, this is going to be really your big formula here. Okay, all right. You're going to be using this relationship. You're going to go to figure out the moles. You're going to be, so you know, if you're given a certain molarity of a solution, and you know its volume, you can figure out how many moles it is. And then this will be in a chemical equation, and then you can figure out, use the recipes to figure it out. So this is really going to be a big deal. Now, so now let's say we want to find out how many mils of a solution do I need to get 3 moles of 5 molar NaCl. So this is going the other way. So this one is that, so you're given, you're having a certain amount of moles, and then what you want to do is find out volume. Okay, and so again, you're going to use molarity to figure this out. Right, so molarity is the key guy from going from moles to volume, and volume to moles. Okay, so so if you want to go from volume to moles, okay, you'd be multiplying by the molarity. And then in this example down here, where you're going to go from the other way, you're going to be dividing by the molarity. Okay, so let's see how that works. So I have 3 moles of 5 molar NaCl. Okay, so first I want to figure out, so let's see how it works. So I change the big M to moles per liter, and then I simply, you could set up dimension analysis. You got 3 moles times the conversion factor, and then you get 0.6. Okay, or you can do just what I just said over here. You could take 3 and divide it by the the molarity. So, and you get 0.6 as well. Okay, so so you can figure out moles from you can go from moles to volume by dividing by the molar mass, or you can go the other way to figure out the volume. Okay, so it's similar to molar mass. It's mass to volume. Mass to moles using molar mass. For molarity, there's a simple relationship, and that's for aqueous solutions. Sorry, get it straight. We use molarity, and so if you start out with the volume, you can figure out moles by multiplying by the molarity. And if you have moles, you want to figure out volume, you divide by the molarity. And the last slide of this presentation is I'll write down all the relationships, sort of the quick ways to come up with your. So let's do one more of these, and this time we're gonna get mass as well. So how many grams of sodium hydroxide do we need to make 500 mils solution of 1.7 molar sodium chloride? So a lot of times in a problem, you're going to have you'll have a solution, and you're going to have to figure out the grams. Okay, and so you'll start out with moles, and then you'll have to figure out how many liters that is. Okay, dividing by the molarity. Okay, and then sorry, the other way around. So you'll be given liters or milliliters or whatever volume, and you figure out how many moles that is. So you'll be multiplying by the molarity. Okay, and then to figure out grams, you simply multiply by the molar mass. And that's what we're doing here. Okay, so first thing I want to do is I want 500 mils to be 1 liter. And I want the molarity be to be moles per liter. So so again, a lot of this, is we use dimensional analysis and so forth. I mean, you would take 500 mils, and then our ratios or grouping, 500 mils times 1 liter over 1,000 milliliters is equal to 0.5. Okay, again, once you get okay, my cat's making strange sounds. All right, he does that whenever he gets done eating or when he wants to eat. He wants to let everybody know. Okay, so once you get kind of good at this, you automatically know what 500 mils is. It's a half a liter. And you could just think about it. A liter is a big container, and mils are little, and so there are 1,000 mils in 1 liter. So it makes sense that there's 500 mils in a half a liter. And so, definitely do the conversions if you need to do them, but make sure you get the right units and the right answer when you do these. Okay, so first thing I want to do is I want to find out how many moles sodium hydroxide are in a half liter of 1.7 molar. Okay, so I know there's 1.7 moles per liter, and a half a liter is obviously going to give me 0.85 moles. You can set up as dimensional analysis. I hope you just heard what I said. So 1 liter has 1.7 moles, and you just split that in half, you'll have 0.85 moles. Okay, right, so that's how you can just do by thinking about it. But again, it's good to show your work. So 0.5 times the molarity, get moles. Okay, so remember what I told you is that volume times molarity will give you moles. Right, so now I have moles, and now I want to figure out how many grams that is. Well, simply, if I know the molar mass and I have the moles, I multiply the moles by the molar mass and I get 34 grams of sodium hydroxide. Okay, so these are the 3 typical operations you'll have. You'll go from liters to moles. Okay, multiplying by molar mass, you go from moles to liters, divided by molar mass, and if you figure out grams, you would go liters to moles to grams. Okay, or you might have to go the other way, go from grams to moles to liters. Okay, all right, so think about. Okay, so the next thing with solutions is that the last set we were mixing soluble solids into water to make aqueous solutions, but you can also take soluble liquids and mix them into water to make aqueous solutions. For instance, when we buy acid like hydrochloric acid, it comes as super concentrated. It's 12 molar. Okay, 12 moles per liter, which is very, very dangerous and impractical to use. So what we like to do is dilute this so it's at a concentration that's easier to work with, maybe like 3 molar. So let's go over how I would make a 3 molar hydrochloric acid from 12 molar, and specifically, let's say I want to make 1 liter 3 molar from 12 molar. And so I have, let's say I have like, a 20 liters barrel of 12 molar. And this doesn't matter up here. Okay, so hopefully you see that I want to dilute the solution. So 12, I want to dilute that to 3, so I'm going to dilute it by 1/4. So my final solution is going to have a strength, well, strength is actually the wrong word, concentration, that's 1/4 of my original. All right, to do this, you would take 0.25 liters of your 12 molar, and then what you would do is add enough water to get it to 1 liter, and then you would have 3 moles per liter, and it'd be 1 liter, just like you said. Now, just to give you some practical thoughts, and if we did this in the lab, we would do this actually do this in lab. One thing you never do is you never put measure out acid, okay, and then add the water, okay. So I actually did this, the way I wrote this out was wrong. The way that I would do this, you never add water to acid, okay. You always add acid to water. So the way that I do this, okay, let's say I have a 1 liter beaker or a 1 liter container measured to 1 liter. What I would do is I'd add some water, maybe like half a liter, okay, of water, okay, and then I would add the acid. So then I would add 250 mils, which is this, 250 mils. Okay. Then you add the acid. And you go up to here. And then you'd add enough water to get to 1 liter. Okay, if you put the acid in first, and then the water, you get a very quick, nasty reaction that could actually explode and break the beaker, and you don't want to do that. Okay. All right, then this is the practical way of doing it. Okay, so you always add acid to water. You never add water to acid. And that's typically how you do any of these, is that you will always add your solute to some of the solvent, and then you get your final volume by adding the rest of the solvent to get the proper volume. No, darn, this previous problem actually took some thinking, you know, and you should always be able to think about it. You should be thinking about your answer, but a lot of times in chemistry, just like, you know, going from grams to moles, moles to grams, okay, so if I want to know how many, I want to go from moles to grams, I'm going to multiply the molar mass, okay, and I can tell you why that is. I can actually think about it and tell you why that is, all right? But this is a quick way of doing it. Say moles times the molar mass gives me grams. You know, or if I want to go from liters to moles using molarity, I'll multiply by the molarity, okay? So these are quick ways. There's always quick ways of doing getting your answer in chemistry. But you should always be able to think. Your answer should always make sense. And one of the problems with chemistry is that there's always a quick answer that you could skip thinking. One thing I like about grouping is it's a thinking process that includes math. But sometimes, you know, after doing this so many times, you kind of just want to get an answer. And so that's often called quick and dirty tricks, formulas. And we saw that with like figuring out the ionic formulas, you know, the crisscross. Crisscrossing is a quick and dirty trick. So we have a quick and dirty for solutions, dilutions of solutions. And here's the formulas that we use. M1 V1 equals M2 V2, or C1 V1 equals C2 V2. All right, so C1, C stands for concentration, M stands for molarity. Molarity is a type of concentration, so we can either use C or M. Since we're dealing specifically with molarity, you can just use M. M1 is your stock solution or your super concentrate, or the 12 molar in this case. V1 is the amount of your stock solution that you're gonna take to get your final concentration. M2 is the final concentration in molarity, and you could use C or M. And then V2 is your final concentration. So my final concentration is going to be 3 molar, and my final volume is going to be 1 liter. So the thing I'm going to have to find here is the volume of my concentrate, and I'm going to add. So it's more than just plugging everything in an equation and then coming up with the answer. It does take some thinking. So let's use the example above. So we want to find how much of stock solution, the 12 molar hydrochloric acid, do we take. How much of this do we take from the stock solution to make up my final concentration? So again, we're going to find out V1. So I'm going to use this equation, solve for V1, we get that. Plug in 3 molar, 1 liter, 12 molar, and it says I'm going to take 0.25 liters of stock. All right, and so what this means is I'm going to take 0.25 liters of my stock, and then I'm going to have 0.75 water, liters of water to it to get a final volume of 1 liter of 3 molar HCl. Okay, and again you add the acid to the water. All right, and then bring it up. Okay, so it does take some thinking, and you just can't come up with 0.25 and stop there. This tells you how much of the stock you need, and then the rest of it is water. Okay, so there you go. So those are the 4 states and how we're going to go from moles to their measuring. And so let's put this all together. And this, you may want to have this available to you as you get used to it, okay? Because in the next videos we'll be applying it to stoichiometry. So if you have solids, you're going to be using molar mass. And again, going from moles to grams, you multiply by the molar mass, and grams to moles, divide by the molar mass. And that's a 1 step. And make sure you understand, get the right units, understand what you're doing. You can use dimensional analysis, you can use ratios, but make sure you show your work. Just, if I say how many moles, how many grams is, so if you, let's say I have 2 moles of sodium hydroxide, and I ask you how many grams that is, and you just write down 40 grams. Okay, well, I mean 80 grams. Okay, that's the right answer, but you didn't show me how you got it. All right, so make sure you show me how you get your answer. There's 2 moles. Every mole is 40 grams. So you could just say 2 moles times 40 grams, or 40 grams 2 times, or using dimensional analysis ratio. Okay, make sure you do that. All right, for gases, the measuring unit is usually liters. If it's milliliters, you have to go to liters. You're going to use the ideal gas law, and then what you're going to do is rearrange the equation for either N. Given V, you figure out N, and if you want to follow, have moles to volume, you have N, and you go to V. Again, that's 1 step. Right. And again, this is assuming that pressure and temperature are constant. All right, for liquids, we measure volume, and the volume could be, it's usually going to be milliliters, but it could be liters or any other volume. It's going to require two steps. You need density and molarity. Okay. So first thing, so let's say we want to go from volume to moles. It's two steps. First of all, you got to figure out mass using density. Okay, and again, you could use dimensional analysis. And then moles to mass to mole. Then you have the mass. You can figure out how many moles that is. So you can divide by the molar mass. All right. Now, if you want to go from moles to volume, again, you have to do figure out how many grams that is. So you multiply by the molar mass. Then from mass to volume, we use density. In this case, you'll be using divide by density. All right. Okay, and the final state is aqueous solutions, and you can use molarity. Again, this is one step. This is a two-step. So solids and gases and aqueous solutions are usually one step, going from volume to moles. So volume to moles, you multiply by the molar mass, and moles to volume, you divide by molarity. Multiply by molarity and divide molarity. One step. Okay. Okay, so now I'll give you some problems that you work with this, and they won't be due, but I'll give you the answers to them. And then what we're going to do is we're going to move on and use this actually in stoichiometry. So we'll be combining our idea of moles with recipes with actual measurements.